Okay. So, welcome back to week 8 of problem solving sessions for this course on applied statistics and econometrics. I am Shreya and I am the TA for the course. And today I'll be discussing a few problems related pertaining to the lectures and concepts that were discussed in week 8 lectures. So before that, any doubt from the previous lectures, previous doubt clearing sessions, anything? If you have, please tell me.
No, ma'am.
Okay. So if there's nothing, then I think we can start. Alright. So I'll just briefly touch up on what was discussed. So in this week, we got to know how to conduct hypothesis testing in a regression setup where we had some regression model, let's say of this form, plus error, and we had some set of assumptions on the errors. So do you remember what were the assumptions? So our first assumption was that the x's were fixed and non-stochastic. These were not random variables. These were fixed and known variables. Then we also assumed that expectation of the errors given the explanatory variables, those are 0. All the errors are have equal variance, that is the assumption of homoscedasticity. And we also assumed that the number of estimated parameters or the number of regressors should, or specifically the number of estimated parameters should be less than the total number of data points, that is n should be greater than p, where p is the number of parameters to be estimated. So under all of these conditions, we derived the ordinary least squares estimates of the parameters beta naught, beta 1, beta 2. Now we are interested to see if the variables that we are considering in our model, they add value, or are they sufficiently enhancing the prediction that we are obtaining for y. So for that, if we have a single parameter testing, like for example if we want to test if beta 1 equal to 0, then we would go for a t-test. Now we should bear this in mind that there is a relationship between a t and an f statistic. So a t, if we just do a t square with degrees n, then we would get a f1n statistic. Okay, so this relationship holds. So instead of using t-test for testing a single parameter, we could also use an f-test. Okay, but the numerator degrees of freedom would be 1 and the denominator degrees of freedom would be that degree of freedom with which we are conducting the t-test. Is it okay? Alright, so then we also learned how to carry out testing when we have a linear combination of parameters. Like for example, if we have beta 1 plus beta 2 equal to 3, in such cases also we can transform this equation. Instead of writing both beta 1 and beta 2, we can write beta 2 or beta 1 in terms of the other one, and what we are doing in that way, we are saving on the degrees of freedom, because if both of these are related in some way, then instead of using both, if we do some sort of transformation, we will have less number of parameters to be estimated, and that can prove to be beneficial. Okay, and then we also got to that restricted unrestricted setup where we could test multiple linear restrictions using f-test, and also testing the overall significance of the regression. So when I say overall significance, I mean to say is beta 1 equal to beta 2 equal to 0. All the regressors that are contributing to the model If all coefficients are set to 0, then none of the regressors are significant to the model, versus the other h0 will be either beta j not equal to 0. So if we want to test for the significance of the regression model, whether the model that I am considering is actually beneficial or not, for that we have to do that overall significance of a regression test. And we have seen the statistic that has been used. So it was basically r square by k by 1 minus r square by n minus k minus 1. So if you remember, where k is the number of regressors in the model, not the number of parameters but number of regressors. Like for this example, how number of parameters, if I denote it by p is 3, beta naught, beta 1, beta 2, but k is 2 because we have only two regressors, x1 and x2. Is it okay? Any doubt? All right. Okay. So then we also learned about a few model misspecification issues. We got to know about the omitted variable bias. So what happens if we have an important variable to be considered in our model, but for some reasons due to ignorance or due to lack of availability of data, we are not able to account for those kind of variables in the model. Maybe because we don't know that this is significant to the issue that we are addressing, or maybe because it is something related to it's very cost intensive. Let's say data collection on this variable is very cost intensive. Then in those situations, what we do, we go for some sort of proxy or instrumental variables, and using them we try to deal with the model misspecification error issues. Then apart from that, we also learned about this regression equation specification error test, or the Ramsey reset test, which provides justification as to or it is a test which we conduct in order to validate that the linear model that we are using is okay and there are no non-linear forms. The non-linear form of the equation, functional form, is not true. So whatever regression we are doing, we are not misspecifying the underlying functional form which is non-linear by a linear thing. So what I mean to say is the relation between the dependent and the independent variables, they are like there are no non-linear forms to it. It's a linear kind of a relationship, and linearity in terms of parameters. Okay, and then again we learned about the heteroscedasticity problem. So if you remember, during OLS we had this important or during in Gauss-Markov theorem we had this important assumption that variance of epsilon I equal to sigma square for all I, that is all the error variances are equal. But if in case the error variances are unequal, so the importance of this thing is, if this holds, then we know that the OLS estimates are unbiased and the blue, like best linear unbiased estimator among all unbiased estimators. So if this doesn't hold, then we cannot say that the OLS estimators are the best among all unbiased estimators. So, in order to detect and tackle, we learnt about White's test, which would detect the presence of heteroscedasticity, and some sort of solutions like using the weighted least squares formula or some other correction which would give us the heteroscedasticity adjusted uh, by variance. So those kind of calculations also we saw in this week lectures. So with that context, I would like to move on to the solutions of week 8 assignments, and then a few problems based on whatever was discussed in these lectures. So I don't think there's anyone here to ask questions, so I'll just proceed. So this is the first question. So suppose we have the following regression model, and this model is estimated using 33 observations. So n in this case is 33. So number of unknown parameters p is 1, 2, 3. Okay, and k number of regressors is 2. Now we have to test h naught beta 2 equal to 0. So appropriate critical value for this thing. So we know this is we have to do a t-test. So if we are to do a t-test, then we know the t-statistic is beta 2 hat divided by standard error of beta 2 hat. And this under h naught is going to follow a t-statistic with n minus k minus 1 degrees of freedom. Okay, so here we have, so the t critical value will then be t. We are doing a two-sided test. So the two-sided test, the rejection region will be, we will reject h naught if and only if probability of t observed greater than t critical okay. This should be less than 0.05. Is my screen visible? Hello? There seems to be some issue. Okay. So what I was saying, this is the p-value format. We would reject if t observed or t stat. So there are two ways to go about this thing. either we can follow a p-value approach or we can follow a critical value approach. So I think I'll follow a critical value approach here. It is easier. So we'll reject H0. Here H1, one second. Okay, so H1 is beta 2 not equal to 0. So we are going to reject H0 against H1 if and only if the observed T is either greater than T n minus 1 n minus k minus 1 0.05 or T observed is less than minus T n minus 1 k minus 1 0.05. So this is a T distribution which is symmetric about 0. This point is T n minus k minus 1 0.05, that is area above this line is 0.05. Similarly, this one is symmetric about 0, so minus T n minus k minus 1 0.05 is that point. If this is something, it will be minus that thing, below which the area is 0.05, so that 0.25, I'm sorry, so that the total area is 1. So then the appropriate critical value is this thing. So T 30 0.025 is this thing. We'll see from the chart. So here we have this one 0.025 and the degrees of freedom is 30, that is this one. So then we are going to come here and this one is also this thing. So the intersection is 2.042. So then the critical value is this one, 2.04. And the other critical value which is not listed, if minus 2.04 was there, that was also a critical value. So or if I can rephrase this thing, the rejection rule is modulus of T observed is greater than T critical, that is T n minus k minus 1 0.05, which is 2.04, because this is T30, I'm sorry, this is 0.025, that is T30 0.025, which is 2.04. Okay, is there anyone? Not yet. Okay, so I'll just proceed to the next one. So let us consider this model which was estimated using 1000 observations. We have n equal to 1000, k number of regressors 1, 2, 3, number of unknown parameters 1, 2, 3, 4. Okay, which would be a possible restricted regression to test the null hypothesis beta 3 plus beta 4 equals to 1. So we have been given one restriction. So as I was saying, instead of using both beta 3 and beta 4, we would substitute either one here. So let us substitute beta 4 in terms of beta 3. So what we would have is yi yi equals to beta 1 plus beta 2 x2I plus beta 3 x3I plus, instead of beta 4 I am going to write 1 minus beta 3 x4I plus ui. So this one we can write as beta 1 plus beta 2 x2I plus beta 3 x3I plus x4I minus beta 3 x4I plus ui. So this thing we can take on the left hand side. So we would have xi minus yi minus x4I equals to beta 1 plus beta 2 x2I. Beta 3 will take common from here, x3I minus x4I plus ui. So this then becomes, this thing becomes my transformed regression equation. So what is the benefit? If instead of regressing yi we just subtract these things and subtract x3 and x4 also, then we, with the same number of n's, we are having more degrees of freedom for the estimation of errors. Why? Because we are, instead of having 4 unknown parameters, now we have 3 unknown parameters, and with that we are going to, so this one we'll call it as some y star, this one will be some x3 star. So instead of 4 unknown variables, we are having 3 unknown variables right now, and thus we are saving on degrees of freedom, which will give us more accurate or it will provide us a better estimate of this thing, the error. Alright, so we'll move on to the next one. Meanwhile, I'll just check if there's anyone. Okay. Fine. Screen is shared. Alright. Okay. So moving on to the third question. We have been asked to consider the following model. And which of the following null hypothesis could be tested using an F-test? So we have to keep this in mind that for an F-test we need to have linear restrictions on the parameters. So what I mean by linear restrictions is that all of these tests that we have done is basically were linear in terms of parameters. So we always did beta 1 equal to 0, beta 1 plus beta 2 equal to 0, beta 1 equal to beta 3 equal to beta 4 equal to 0, something like this. But for testing interaction terms, we did not use F-test. So we cannot, and this is also a squared term. So this one and this one cannot be tested using a F-test. Yes. And this one if we have option C, then beta 4 equal to minus beta 3 boils down to beta 4 plus beta 3 equal to 0. So these sort of things we have done using t-test. Also beta 2 equal to 0 we have conducted using t-test. And also I told there is a relation between this one. T square n will be 1 if with 1 and n degrees of freedom. So these tests that we have conducted with a t-test or an f-test. So this one could be also done by an f-test, like imposing the restricted versus unrestricted model. And this one also can be performed because of this relation between t and f statistic. So options A and C are correct. It's okay. Moving on. Suppose that the true population model is given by y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus u, where beta 1 beta 2 not equal to 0, but the covariances between the error terms and the regressors are 0. Now if we consider omitting x2 and estimate this model, the OLS estimator of alpha hat will be biased or unbiased, and inconsistent or inconsistent. So we'll first write down alpha 1 hat. So alpha 1 hat can be written as y minus y bar x1 minus x1 bar by summation x1 minus x1 bar whole square. Now expectation of y from this model, the true population model, is beta naught plus beta 1 x1 plus beta 2 x2 plus 0. But from here we are considering from this model. So the thing is, when we are calculating expectation of y, we would have alpha naught plus alpha 1 x1 plus expectation of epsilon so this one will be so this will be alpha naught plus alpha 1 x1 plus some beta 2 x2 plus 0. Alright. Now this term is going to remain and it will not get cancelled, and that would if beta 2 is not equal to 0. So that is why this will remain biased. Now Now, if we have to see that it is consistent or not, first we have to find out the estimates. So y we have here as alpha naught plus alpha 1 x1 plus something epsilon. So alpha 1 hat will be, the sample estimate will be summation y minus y bar x1 minus x bar by summation x1 minus x bar whole square. Now, in limit, consistency means that something as n increases, it goes as n tends to infinity, the sample value, the variance of these things should go to 0. So, in limit sense, this one, in probability, this one would go to covariance between x1 and y by variance of x1. So that we can write as covariance of x1, and in place of y is the true population thing. So here we'll write the full model. It is beta naught plus beta 1 x1 plus beta 2 x2 plus u divided by variance of x1. So that will become this will be, if we split it, covariance of beta naught is a fixed quantity. That is a true intercept. So we would have covariance between x1 1 into beta naught by variance of x1 plus beta 1 covariance of x1 which can be written as variance of x1 by variance of x1 plus we would take beta 2 out, beta 2 covariance of x1 x2 by variance of x1 plus covariance of x1u by variance of x1. Now this term is 0, it has been already given, and this is a covariance between a variable and a constant. So this term is also 0. So what we essentially have is beta 1, this variance x1 cancels. We have beta 1 plus beta 2 covariance of x1 x2 by variance of x1. So p lim of alpha 1 in limiting sense, this is going to beta 1 plus beta 2 covariance of x1 x2 by variance of x1. Now unless beta 2 is 0, we would not, the alpha 1 hat would not in limiting sense go to the true beta 1 hat parameter. So alpha hat thus is inconsistent. Okay, so the correct answer is, it will be biased, and inconsistent. Moving on. Okay, I have someone here now. Okay, so we have data on 4 variables and the following model was estimated, and their standard errors are given in parentheses. So this is the predicted equation. This is the R square from the model, and we have data on 14 observations. So if we have to find out the t statistic to test the null hypothesis that the coefficient of x1 is 0, the t stat would be beta 1 hat by standard error of beta 1 hat. So this will be 0.1548 divided by 0.03194. So this would come out as anyone? So this would come out as 4.846. Is it okay? So moving on. Okay. Now we have the same thing. Now we have to find out if we can reject the null hypothesis that the coefficient of x2 is 0 against two-sided alternative at 5% level of significance. So to test a coefficient of x2, that is beta 2, this one we have to test if it is 0 or not. This is beta 3, this is beta 1, let's say this is beta naught hat. These are estimates, so I'll just denote them by hat. So this test will be, the test statistic will be beta 2 hat by standard error of beta 2 hat. This will be minus 21.5875 divided by 27.02933. So this would come out to be minus 0.798. And the t critical value, so as I said, the rejection rule is we'll reject H naught if and only if modulus of t observed is greater than t n minus k minus 1 0.025. So here k is the number of regressors. So we have 1, 2, 3 regressors, and another one is for the interceptor, and n is 14. So n minus k minus 1 is n minus 3 minus 1, that is 10. So we have to find out the value of t 10 0.025. So if we go to the t table now, we have to find out this point. Okay. So for here the degrees of freedom now we want is 10. This is the row that we are focusing on. So then this is the value 2.228. So the F critical is 2.228. So do we reject the null hypothesis? Because modulus of t observed is modulus of minus 0.798, that is 0.798, which is less than 2.228. So we do not reject H naught at 5% level of significance. Is it clear? All right. So moving on. Now they have asked, find the critical F value at 5% level of significance. So if nothing is mentioned, then critical F means overall significance of the regression. So for that, the test statistic is r square by k by 1 minus r square divided by n minus k minus 1, where k is the number of regressors. So here n minus k minus 1 is 10, k is 1, 2, 3, 3. So this would be 0.835976 by 3 divided by 1 minus 0.835976 divided by 10. How much are we getting this? Okay, so while we calculate, here the question is find the critical F value. So the F critical is the degrees of freedom k n minus k minus 1, that is F3 10, and this is always going to be right till, that is 0.05. So we'll go and check the F table. So this is the F table, such that these numbers are those cutoff points above which the area is 0.05. Okay, so probability x greater than F numerator denominator greater than the individual values, let's say 3.46 equal to 0.04, or probability F18 greater than 3.46 equal to 0.05. So here we have to find out F310. So degrees of freedom in the numerator 3, degrees of freedom in the denominator 10, and this probability. These are the probabilities. Okay, so here I did a mistake. This probability is 0.1 because it corresponds to this row. Okay. Alright, so we have F310 and we want 0.05. So then we'll focus on this one, 0.05. That is 3.71. So the F critical value that we want to focus on is this one. So I'll just erase this for the time being. So F critical was F3 10 0.05. So this was 3.71. So is the model significant overall? So for that the test statistic was r square by k by 1 minus r square by n minus k minus 1. K, as I was saying, is 3. That is the number of regressors. So we'll just compute this thing. 0.835976 divided by 3 by 1 minus 0.835976 by 10. How much are we getting this? Can you calculate?
$16.98.
Okay, so this one comes out as 16.98. And what was the F critical? F3 10 0.05. That we got from the previous slide, 3.71. So is the overall model significant? What should we conclude? Okay, so the overall model is significant because we were testing H naught beta, this is beta 1, beta 2, beta 3. So what we were testing was beta 1 equal to beta 2 equal to beta 3 equal to 0. All are 0. All zeros means it is not significant. None of the variables are contributing to the response variable. Versus H1 is not H0. At least one is non-zero. So here, since our F observed is greater than F critical, we will reject H0 and conclude that the model is significant. Why? Because we were testing if all are 0, but it's not true. All are not 0. So could be that some are 0, that then we can go for those partial tests, but all are not 0. So which means that the model is significant overall. Is it okay? All right. So then I'll move on to some other problems. Till now, is there any doubt? Okay. So we have been given some income data and possible two regressors or predictors of a person's income. So how many data points we have? First we are going to check, and then we have to test for the presence of heteroscedasticity. So for this we are going to use whatever we have learned, that is the White's test. Okay. Now the advantages of this test was that it does not require normality assumptions, and it also takes into account some non-linear form into account. So we'll see as we proceed. Okay, so for testing for the presence of heteroscedasticity, how would we proceed? So the first thing is we have to fit a model income equal to, let's say, beta naught plus beta naught education. I'll denote this as x1 and I'll denote this as x2, plus beta 2 job experience. Let this be my y. So we have y equal to beta naught plus beta 1 x1 plus beta 2 x2. We have been provided with this table. Now how are we going to calculate beta naught, beta 1, beta 2? That is the first step. So step 1, okay. So step 1 is to calculate this thing, y equal to beta naught plus beta 1 x1 plus beta 2 x2. We have to get beta naught hat, beta 1 hat, beta 2 hat. So how are we going to get it? We have to first write down this model matrix. Now this one, how we are going to fill up? The first row, first column will all be 1. How many 1 will be there? The total number, how many total rows or samples information has been given. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So my n is 20. So 20 times I am going to fill up this row column. Then this is my model matrix. So then we are going to fill up the x1 column. So here I would have 2, 4, 8, 8, 8, 10, 12, 12 and so on. Whatever is there, this thing. And then I'm going to fill up column x2. That is 9, 18, 21, 12, 14, 16, 16 and so on and so forth. So that will be my x matrix. My y vector will be the income column. 5, 9.7, 28.4, 8.8, 21, 26.6 and so on. So once I have written this x and y in vector form, I will also write beta as beta naught, beta 1, beta 2 in this format. So once I have written my entire data in this format, I am going to apply the OLS estimate. So x I have that 1, 1, 1, 1, 20 times. This row will be 20. Here I have the x1 populated values. So as I was saying, let's say 2, 4, 8 and so on. 2, 4, 8, so on. And this one was 9, 18, 21, 12. 9, 18, 21, 12. This was the x2 value. And y also I'll jot down the entire dependent column, 5, 9.7, 28.4 and so on. 5, 9.7, 28.4, so on. and beta I would have it like beta 1, beta non, beta 2. So then we can write this as a y equal to x beta plus epsilon. So then beta hat would be x prime x inverse into x prime y. This is the OLS estimate, how we are going to calculate. So how x transpose x would be, so if I have here, let's say x is 1 1 1 1 1 20 times, then we have 2 4 8 something something, and here also we have 9 18 21 and so on. So x prime x would be the entire thing, I'm going to write it as transpose. So here I'll have 1 1 1 1 1 20 times. This I'm going to write 2 4 8 and so on. This I'm going to write 9 18 21 and so on, and we'll multiply it with the original x matrix. 1 then 2 4 8 so on, 9 18 21 so on. So how we are going to do matrix multiplication? This one into this one plus this one into this one, this one into this one. So the first one will be 1 into 1 plus 1 into 1 plus 1 into 1 20 times. So we would have something 20. Also we'll note this has 3 into 20. This is the dimension, 3 rows 20 columns, and this one is how many? 20 rows 3 columns. So finally we would have a 3 cross 3 matrix. Similarly for this position, what we are going to do, 1 into 2 plus 1 into 4 plus 1 into 8 and so on, we would have some number here. For this one also, what we are going to do, 1 into 9 plus 1 into 18 plus 1 into 21 so on so on. So this will be summation x1, this will be summation x2, this will also be summation x1, this will also be summation x2. For this one, what we are going to do, 2 into 2 plus 4 into 4 plus 8 into 8. This one will be summation x1 square, this one will be summation x2 square, this will be summation x1 x2, summation x1 x2. Something we would have like this. We would have a matrix like this. So finally, I have done the calculation in order to save some time. This would be my x prime x matrix, 20 to 41 to 53. How you are going to calculate that I showed here. Okay, plain matrix multiplication. Now we need this beta hat is nothing but x prime x inverse into x prime y. So we'll calculate the inverse of this 3 cross 3 matrix. It will come out to be this one, and x prime y is same thing if we have to do x prime y. So if I go here, x prime will be 1 1 1 1 and so on. This will be 2 4 8, this will be 9 8 21 x prime with a dimension of 3 cross 20, and y would have that income variable, that is 5 9.7 28.4, 5 9.7 28.4. So then what we are going to do, this one will be 1 into 5 plus 2 into 9.7 plus 1 into 37.4 and so on so on. We would have this x prime y matrix of order 3 cross 1, because we have 3 rows here, 20 columns, 20 rows, 1 column. So ultimately we would have a 3 cross 1 vector. That's what we have. I'm sorry. So this is the 3 cross 1 vector that we have. Now we are going to multiply this one and this one, and ultimately we would get beta hat as this thing. So the original equation was income on minus 7.0968553 plus 1.933. I'll just write it in round it up to certain decimal places and then I'll write. Okay, so this one is 0.96 0.97 plus 1.933 into x1. x1 was my education, plus 0.649 into job experience, or we will write y hat equal to minus 7.097 plus 1.933 x1 plus 0.649 x2. So now we have our step 1 is complete. We have regressed the original regressors in the model on my dependent variable. Now step 2 is to get squared residuals. Okay, so we have the models over here. So our model was y1 equals to what was the model? Minus 7.097 plus 1.933 x1 plus 0.694 x2. So substituting these values here, we would have y hat. So residual, how we are going to calculate is that, so for this one, let's say the y predicted for the first one, I am doing it for the first observation. Okay, so the y predicted for first observation would be minus 7.097 plus 1.933 into 2 plus 0.694 into 9. How much are we getting this? Can you please calculate? So we are getting this as something 3.015. So the residual will be 5 minus 3.015 and that whole square. This column is residual square. Similarly, we would get y predicted for the second observation as something minus 7.097 plus 1.933 into 4 plus 0.694 into 18. Whatever value we get, let's say we get it something p star, we are going to subtract 9.7 minus p star and then do a square and keep this column ready. Okay, this is the residual squares that we need. Apart from the residual squares, we would also take square of the original variables, that regressors that we were having. So here we would have x1 square, let's say this is 4, 16, so on. x2 square 81, then this will be 254 and so on. And x1 into x2, we'll also have the cross product terms. So 18, this will be 72, sorry, this is 324, I'm sorry. Okay, and so on and so forth. So now that we have our squared residuals and these variables as well, now step 3 will be, so once we have step 2, Step 3 will be, we would regress residual square on certain alpha naught plus alpha naught x1 plus alpha 2 x2 plus alpha 3 x1 square plus alpha 4 x2 square plus alpha 5 x2 x3. So what we are going to do is that from the new table, this will be my new response. That I am going to regress on the original variables plus their square terms and all possible pairwise interactions. Okay, so once we have done that, then we'll fit this model. Again we are going to get that X matrix. So X matrix this time will be, first column is 1, this will be the x1 column, this will be the x2 column, then we would have x1 square, we would have x2 square, and we would have x2 x3. So similarly we would proceed to x transpose x inverse x transpose y, and we would have a beta hat with, or I would rather say an alpha hat with alpha naught hat, alpha 1 hat, alpha 2 hat, alpha 3 hat, and alpha 4 hat. Okay, so this model, from this model we have, so this one was residual square on x1, x2, or I'll write the regression equation form itself, alpha naught hat plus alpha 1 hat x1 plus alpha 2 hat x2 plus alpha 3 hat x3, sorry, x1 square plus alpha 4 hat x2 square plus alpha 5 hat x1 x2. Once we have this from the equation, so this one is alpha naught hat, this one is alpha 1 hat, this is alpha 2 hat, this is alpha 3 hat, this is alpha 4 hat, and this is alpha 5 hat. So once we have this regression equation, from here we can calculate the residuals from this model. So if we name residual square from the original model as some y star, so if we name this model, this column, if we name as some y star, then y star minus all the predicted y star, substituting all alpha values here and all x1, x2, x1 square, x1, x2 values here, we would get something like this. So then this part would give me the residuals from this augmented model. So if we do a sum of squares of residuals from this augmented model, then we would get sum of squares of errors from augmented model. Also we would get sum of squares of total, that is summation of yi star minus yi star bar, the mean, from the augmented model. So what I am saying is that this column is now my y star. So each individual elements here minus the total mean of the column whole square, and if we sum it up, that will give us this SST. So once we have SSE and SST, we have to find out R square from this model, that is 1 minus SSE by SST SSE of augmented model, SST also of augmented model. So with all the calculations in this current scenario, I have made all the calculations and the R square value. So SSE here comes out as so so SSE was 2755.93 by the total was 5000.741. Just remember this SST is with respect to Y star from the augmented model. That is the squared residuals that corresponds to the squared residuals from the original fitted model. So this R square comes out to be something around 0.4489. Okay, so till now our calculations are done. Now step 4 is to calculate n into R square. This is our test statistic. So here we have n 20 into 0.4489. So this value is 8.977. We are going to reject H naught. H naught was no heteroscedasticity. Okay. So we are going to reject H naught if and only if nr square is greater than chi square 0.05 with degrees of freedom same as k minus degrees of freedom p minus 1, or degrees of freedom I would say k, where k from the augmented model. So everything now we have to do with terms of augmented model. So k aug I am going to write. K augmented model is number of predictors in the augmented model. So how many predictors do we have in the augmented model? Intercept term is not a predictor. These are the predictors 1, 2, 3, 4, 5. So here k augmented is 5. So we have to find out chi square 5, 0.05. So this value is 10.07. Now since nr square, so I'll just write it here, nr square that we have observed is somewhere 8.977 and chi square 5 0.05 is 11.07. So since nr square is less than the critical point, thus we do not reject H naught and conclude that there is no heteroscedasticity. In the model. Is it okay? So step by step once more if I have to repeat. The first step is regress y on the original variables. So from here we will have the OLS estimates. Okay. Then step 2 is get y minus y hat square. These are the squared residuals. Okay, I'll denote it as ui square. Then step 3 is to regress ui square on all the existing variables, their square terms and their cross product terms. Then step 4 is to get r square and k from this augmented model. K will be the number of regressors that I am going to or forms of regressors that I am going to use. So once we have these information, step 5 is to calculate the test statistic, that is capital N into r square from the augmented model. Step 6 is to check that is the rejection rule, reject H naught if and only if the observed in r square augmented is greater than chi square k augmented 0.05, and the H naught was no heteroscedasticity. Is it okay? Any doubt, any questions? Okay. So then I'm going to move on to the next one. So here with the same data, we've been asked to test if the linear form of the regression is appropriate. So what we'll do, we'll consider the Ramsay's reset test. So how are we going to do this Ramsay's reset test? So here also we'll do the same thing. First, step 1, we'll fit y on x1 and x2. This is the model. We would have y hat as, we have already obtained the variables minus 7.097 plus so on and so on. So we have this equation. So first, or if I write in terms of notation, so we already have beta naught hat plus beta 1 hat x1 plus beta 2 hat x2. This is the predicted equation. Step 2 is to, so from this model we have some sum of squares residuals or sum of squares errors. So how we are going to calculate it? From this model we have to calculate the sum of squares due to residuals, or I'll write it as errors, and I'll denote this as the restricted model. Okay, so how we are going to get, we are going to find out y hat minus y whole square, and then we are going to do a sum. Okay, this will give us a sum of squares errors from this original model. Step 2, we are going to fit an augmented model. What will we have in the augmented model? We would fit y equal to some alpha naught plus alpha 1 x1 plus alpha 2 x2, or I'll write it like this, alpha 1 x1 plus alpha 2 x2 plus some delta 1 y hat square plus delta 2 y hat cube. We could go on for 4, 5, 6. There's no limit to it, but for the sake of convenience, we'll take up to 2. Okay? There's no hard and fast rule as to where we should stop. Alright, so what is y hat? Y hat is, so y hat for the first one will be that here we have calculated y hat for the first one using these coefficients and putting the values of the variables. We would have something y hat predicted. So here the first one was 3.015. so let's say this, the first one is 3.015. so we'll subtract this one from this one, take square, and then sum it up across. We would get sum of squares restricted. Now similarly for step 2 we would fit an augmented model. So using this y hat and squaring it up and cubing it up, if we use those two variables in the model, we would have, this is my unrestricted model. Okay, so once we fit this unrestricted model using the OLS technique, we would have, so after we fit that, we would have something y hat as alpha naught hat alpha 1 hat x1 plus alpha 2 hat x2 plus something plus delta 1 hat y hat square plus delta 2 hat y hat cube, and so on. This would be my fitted equation. So for this model also, let us denote this by some y hat star. Then from this model we would also get some residuals, that is y minus y hat star. We would square it up and take a sum, and that would give us sum of squares error from the unrestricted model. So once we have these two, now we have to test whether this linear form of regression is appropriate or not. So what we have to test, the linear form was up to this inclusion of x1 and x2. Whenever we included y hat square and y cube hat, then the linearity is lost. So in order to test if it is linear or not, we have to set both delta 1 and delta 2 to 0. So the restrictions are delta 1 equal to 0 and delta 2 equal to 0. So here we have how many number of restrictions? Equal to 2. Okay, so then we have to test for this thing. Now as we know that f test, how we are doing f test, we have to do sum of squares error due to restricted model minus sum of squares error from the unrestricted model divided by sum of squares error from the unrestricted model. So the numerator should be divided by the number of restrictions, and this should be the degrees of freedom of errors from unrestricted model. Okay, so let us assume I have the information, these figures I have. The main thing to calculate is the degrees of freedom of error from the unrestricted model. So we have already seen we have two number of restrictions. So we know that this degrees of freedom will be 2. Now we have to find out the degrees of freedom of errors in the unrestricted model. So unrestricted model was y equal to alpha naught plus alpha 1 x1 plus alpha 2 x2 plus delta 1 y hat square as delta 2 y hat cube. So how many unknown parameters did we have to estimate from here? We had to estimate 5 unknown parameters. Okay. So the degrees of freedom of error was total n minus 5. So here n was 20 and number of unknown parameters were 5. So this was 15. So what we would essentially have is f observed will be sum of squares error from the restricted model minus sum of squares error from the unrestricted model divided by number of was 2, number of restrictions delta 1 and delta 2 to 0, and this would be sum of squares due to errors from the unrestricted model divided by the df, that is 15. So let's say I have this information, this is given to me as, so I'll write it here, sum of squares error from the restricted model is given as 282.20, that is from this model, and sum of squares error from the unrestricted model is given as 268.57. So we are going to put it here, 282.20 minus 268.57 divided by 268.57, this above by 2, below by 15. So this would come out to be 0.38. Now we would reject h naught, that is delta 1 equal to 0 and delta 2 equal to 0 if and only if the f observed is greater than f, the numerator degrees of freedom, denominator degrees of freedom, and critical point 215 0.05. Now f 215 0.05 we are going to find out from the table. So 215, okay, I don't have it here, but this value is something close to, I don't have the table figure over here, this is something 3.68, and our f observed, it came out to be 0.38. So the decision, our decision is we do not reject h naught, and if we do not reject h naught means delta 1 is 0, delta 2 is also 0, which means that, and conclude, what should we conclude? Whatever was given in the first sentence, that the linear form is appropriate. Conclude that linear functional form is appropriate. Is it okay? So I am going to repeat the steps one by one. So computationally this might feel challenging, but don't worry, I don't think such complicated calculations will be given in the final exam, but some values might be provided to you based on which you might have to calculate. Okay, so it's better to know what to look for. Okay, so for this Ramsey reset test, what
Excuse me, ma'am.
yes,
The value of the SSE will be given.
I think so, it will be given,
Yes,
because
ma'am.
otherwise calculating it is a little challenging in the examination
ma'am.
hall. So I'm just showing you how it is done,
Okay.
and if these values are provided, hopefully you will be able to solve the problems.
Okay.
Okay, so for reset test, the steps are: first we are going to fit the let's say the original, this is my original regression. Then from here I am going, this will be the restricted model. So from here I am going to get sum of squares error due to restricted model. This is step 1. Then step 2 will be to fit an augmented model. What we'll do, we'll have, apart from the usual regressors, we would also fit the y predicted. So here we'll get this predicted values. So we'll just fit the square terms and cube terms. Then we are going to, step 3 is to test for sorry, I just made some notation thing. I'll denote it with a different notation. It's easier that way. Okay, so plus delta 1, delta 2, delta 1 equal to 0 and delta 2 equal to 0. So this will be my unrestricted model. From here also I am going to get sum of squares unrestricted. We could also even add some other term, delta 3y to the power 4. Then our h0 would be delta 3 equal to 0. And then step 4 would be to get the f statistic, that is SSE restricted minus SSE unrestricted by number of restrictions, total SSE unrestricted by degrees of freedoms of SSE unrestricted. Once we have that, we are going, so once we have this, we are going to check if f observed is greater than f critical. That will have these as numerator df and this as denominator df. If this is true, then we are going to reject. Okay, is the workflow clear?
Okay, ma'am.
Okay, so I'll just move on. So now I will try to give some idea on how we should calculate or get the weighted least squares estimator. So I don't think this has been discussed in the class, but nevertheless I'm going to give some idea so that if questions like these come, then hopefully you'll be able to address it. Okay, so suppose we want to fit a no intercept model. We have only one regressor and one predictor, sorry, one regressor and one response using a weighted least square. So in that case, what we do, let's say we have, this is my regression model. Okay, so weighted least squares, in order to fit a weighted least squares, we would write the summation error as summation some weight into yi minus beta xi. Okay, so in OLS we wanted to minimize sum of squares of errors. In WLS we will just add a weight term over here, and then the procedure is similar. Here we have one unknown, so we'll differentiate this equation with respect to one unknown, and then we'll equate it to 0, and then we'll solve for beta. Okay, so here in this thing we have only one regressor and one predictor with no intercept term. So we just have one thing. So if we just differentiate with respect to this, what we get is that summation 2 wi remains yi minus beta xi into minus xi. So this one we have to equate to 0. So then 2, if you go there, it cancels. Minus 2 also we can put it there. So what we have is 2 yi xi minus beta wi xi square. This thing equal to 0. So if we solve, we would have summation wi xi equals to beta summation wi xi square. So beta WLS will be summation wi xi yi by summation wi xi square. So this is the general formula for weighted least squares estimator. Okay, so now summation wi xi yi by summation wi xi square. Now it has been given wi is 1 by variance of yi, or in other words 1 by sigma I, something like this. Then we have to just, this is the general formula, by sigma I square by summation xi square by sigma I square. So for the timing, just ignore this one, okay, or I'll delete this, that's better, I think. 1 second. So this is a general formula of weighted least squares. Now what was discussed in class is that, suppose, this part is important, suppose the variance of yi is proportional to xi, that is, 1 second, why is it not working? Okay. So variance of yi is C. So we have something like this, yi equal to beta xi plus ui. Now this is given, variance of yi equal to c xi. So variance of yi was variance of ui, which is equal to c into xi. So this is not constant. So what was the way out? The way out was, we divide yi by root over xi. Then what we get? Then we would get beta xi by root xi plus ui by root xi. Now this is my new error term in the transform model. So if I do variance of ui by root xi, then what am I going to get? I am going to get 1 by xi into c xi, and this xi will cancel, and we would have some constant c. So if we call this as some yi star, then variance of yi star equal to c for all I. So this transformed variable then becomes suitable for OLS estimation. Okay, and then, so if in this context we try, and if with the transformed variables we go and try the OLS estimation, then we are going to get the weighted least square estimator. Otherwise, the alternative is to just substitute whatever the generalized value that we got in a single variable case xi yi by summation wi xi square. So we have to note that there is a single regressor here and it's a no intercept model. So here if wi was proportional to 1 by variance of yi, it was 1 by variance of yi and variance of yi is cxi. So then the beta wls will be summation wi is 1 by cxi into xi yi by summation 1 by cxi into xi square. This xi cancels, xi cancels, 1 by cc also is a constant, it will also cancel, and this will be summation yi by summation xi, or we can write it as x bar by y bar. So then the beta wls in this context will be from the origin, from this setup, it will be, we'll just take x bar and y bar and put the values over here and get it as y bar by x bar. Is it okay? This is one way out, or the other way is we transform the variables and then calculate from here. Okay, so if we go that way also, I'm going to show you what is going to happen. So we have yi by root xi equals to beta 1 root xi plus ui by root xi. So this is system yi star equal to beta 1 xi star plus some ui star. So then the OLS model will be summation xi star yi star by summation xi star whole square, which is nothing but xi star is root over xi into yi star is yi by root over xi by summation xi star is xi root xi whole square. This one cancels. This is also summation yi by summation xi, which is y bar by x bar. So the formulas are matching. It's fine. Okay. So again, now in this context, if we have something like this, that variance of yi is k into xi square, then if we have a model like this, if variance of yi is equal to k xi square, then we are going to divide by xi. Then we have yi by xi equal to beta plus ui by xi. Then variance of ui by xi will be 1 by xi square variance of ui, that is 1 by xi square k into xi square, that is k. Here we have constant variance. Okay, so there is nothing to estimate from this thing. So if beta hat is then the intercept term, so then beta hat will be summation 1 by n summation yi by xi. And also if we put these values in that previous, if this is the estimate that we were considering by summation wi xi square, wi is 1 by variance of yi, which is 1 by k into xi square. So putting here, we'll have yi xi by k into xi square divided by summation 1 by k xi square into xi square. Xi square will cancel, 1 will cancel from here, k is a constant, it will also cancel. So we would have summation yi by xi divided by summation into 1, that is 1 by n summation yi by xi. Is it okay? So the main thing that I want to tell you is that whenever we are doing a weighted least square, my weights that I'm going to consider in the model. So let's say if I have y equal to beta naught, now if I have intercept, so my equation will be y minus beta naught minus beta 1 x1 into some square into some weight. This thing we have to differentiate with respect to the unknown parameters, whatever how many we have, equate them to 0, solve for them and get the WLS estimators. Okay, this is for a one variable case, and if we have a multivariate case, then the beta hat WLS will be x transpose WX inverse x transpose WY, where W will be 1 by variance of Y1, 1 by variance of Y2, so 1 by variance of Yn. Okay, and all the others will be 0. Is it okay?
Okay, ma'am.
Okay. So that was all from my side for today.
Ma'am, please explain question number 1 and 2. Actually, I joined late.
Oh, okay, fine. Question number 1 and 2. So 1 was this one, that we have the following regression model which was estimated using 33 observations. We have to conduct a two-sided test for testing this one, beta 2 equal to 0. So for conducting this test, the test statistic, the t-test statistic is beta 2 hat by standard error of beta 2 hat, and under H naught it follows a t n minus k minus 1, where k is the number of regressors. Okay, so the rejection rule is whatever t observed value we are getting, we'll take a modulus of that, that is the if we get something like minus 7.18, modulus will give us 7.18. So that figure should be greater than the upper 0.025, should be greater than this point. So this is my critical point, Tn minus k minus 1, 0.025. Okay, so we are going to, the critical point is n minus k minus 1, 0.025, because they are saying two-sided 5%. Had it been two-sided 10%, we could have taken this as 0.05. Whenever we have something two-sided, this thing for a t-test, we have to do this by 2, but not for an f-test. Okay, so for a t-test we did this 5% by 2, that is 0.025. We calculated this from the t table. So this was the column for 0.025, and degrees of freedom we had 30, so 2.042, that is the critical value. Is it okay?
Okay, ma'am.
Okay, and the second question was this, that we considered the following regression model. It was estimated using 1000 observations. Which of the following would be a possible restricted regression to test the null hypothesis beta 3 plus beta 4 equal to 1? So whatever restricted regression we say, what we do, we try to implement this restriction in our model. So doing that, instead of writing beta 4, I wrote it as 1 minus beta 3, and then this x4 comes out here, and we have minus beta 3 x4. We take beta 3 common here, so we have x3 minus x4, and we move x4 to this side of the equation. So then we have some revised y and some revised x3, let's say. So what we are essentially, this is the transformed regression or restricted regression equation. So what we are doing essentially is that we are reducing the degrees of freedoms of the error in this case, because under this restricted model these two are related. Now if I have to test this one, what we are going to do is that from this original model we are going to get the sum of squares unrestricted. From this transformed model we are going to get sum of squares restricted, and then we are going to apply this f test that we were talking about, sum of squares restricted minus sum of squares unrestricted, sum of squares error, divided by, we had only one restriction, x beta 3 plus beta 4 equal to 1, one relation, one restriction, divided by sum of squares error unrestricted by df of the unrestricted. So here we have 1000 observations, right? And how many are we estimating from this unrestricted model? 1, 2, 3, 4. So we'll take 1000 minus 4 here. This will be the test statistic, and the f critical will be f1 996. And then if this observed is greater than this thing, we will reject this null hypothesis, otherwise we are going to accept this null hypothesis, or we will not reject the null hypothesis. Okay, so for the sake of this question, the answer will be part B.
Okay.
Okay, anything else?
Like ma'am, in question number 9,
Hmm.
we have calculated the value of the beta 0, beta 1 and beta 2.
Hmm.
Question number 9.
Hmm.
So is there any I'm using a starter, can we use
Yes,
starter
you
to
can.
find the value of the beta 1, beta 0,
I don't
beta
think
1
you'll be allowed to
that will-
use it in the exams, but
not in examination.
yeah, for work purpose you
in
can
general.
use any of the softwares. You will
Okay.
get the intercept values, you will get R square. Most softwares will also give you you will have some special packages with which you can conduct these tests even. Okay, so if you use a package, if you use R or Python, they already have some pre-installed packages where you can use these kind of tests.
Okay, ma'am.
Okay. So if there's anything else you can say.
Ma'am, one request also there. In the next Saturday, can it possible that from the week 1 to week 8, can you explain the theory or summary of this?
Actually,
theory
I'm really sorry, but I don't think I'll be able to explain within these weeks, because my task is to like solve the problems for the
no
students who are taking the course. So but I would suggest there are ample material on the internet available. You can go through videos of various software programs, whatever concepts or whatever tests that you have learned over here right now, you will find softwares, and you'll find packages which already implement them. So I would request you to go there. I'm really sorry, I wish I could do it, but I am not as per my instructions I cannot do that.
No problem.
Okay sir.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
Thank you for joining. I'll see you next week.
Okay, thank you.
Mhm.